Okay, this is beginning some notes on light stuff. I apologize for that hissing. I'm recording this from the balcony in a hotel in Orlando, and there's this big fountain in the background. This may be the worst video ever, so just get ready, and it won't kill you. First, light stuff. Can sound travel from here to the moon? Why or why not? Well, sound is a wave, and here's a picture of a boy standing next to a pool with no water in it. And if the boy jumps in the pool right here and he starts to, flop around, there can be no waves in the pool because there's no water. A wave needs something to travel through, and since sound is a wave, it has to have something through which it can travel, and there's nothing in space. Now here's a great picture of the vacuum of space. Clearly there's no big vacuum cleaner in space, but vacuum just means emptiness of space. So sound cannot travel through space. Light can travel through space because light is a little different, and we're going to be getting to that in a minute. So back to that first question though, no. Sound cannot travel through space because sound is just a wave. So I'm going to write no waves must travel through some material. And there is nothing in space. I'll just write space is empty. And I'm going to put space in quotation marks because space just means the area between here and there, but space in the sense that I'm talking about, I mean beyond the Earth's atmosphere. So when you hear astronauts talking to one another, they're talking to one another over radios, and they're not speaking and having the sound travel through the air like it's traveling to your ear from the speaker. This next question, is sound pulled down by gravity? No, that's the short answer. Sound actually curves up into the atmosphere because it travels more slowly. Let's see if I have this right. Sound, let's see. I'm moving on. I think sound curves up instead of down, but it's definitely not pulled by gravity. So this next thing says light is a strange thing. It's a wave, but it's also a particle. How is it like a particle? Light is like a bullet. You can think of light as being, it's called, the little particles of light are called photons, and a photon is a particle of light. Light is also a wave, and we'll get to that in just a second. So how is it like a particle? How is it like a little bullet that comes out of a gun? Light can travel through a vacuum. And I'm just going to write, light can travel through empty space. Early on, we were doing things with springs, and we sent waves through springs. If you jiggle the spring here, the wave moves down the spring. And it's not the metal that actually moves down the spring, it's the energy that moves down the spring. In the case of light, you don't need a spring, you don't need anything. Light can just travel through empty space, so it's like a bullet. It's like you have some mass moving through empty space. Not exactly, but sort of. Light is very confusing. The other way light is like a particle is that light is pulled by gravity. And that's why there's such a thing as a black hole. If something has enough gravity, it can pull light in, and light can never get out. That's not the case with sound. You couldn't have sound traveling past a black hole because there would be no air for the sound to travel through. But if you could, the sound wouldn't really get pulled toward the black hole. The air would, and I guess the sound would go with it. But when I'm speaking right now, my sound is not getting pulled toward the earth, but the light that's traveling to this paper is just a little bit getting pulled toward earth. So light is like a particle. It's like a little bullet in those two ways. It can go through empty space and it's pulled by gravity. On the other hand, it's also like a wave because light has a wavelength. And if you look farther down the page, you can see there are all these pictures of different transverse waves. Light's like a transverse wave. And you can see a lot of different wavelengths down there. And then I'm going to say, this is sort of cheating because I've got two dots, but this second dot is going to be a bunch of stuff. Light exhibits other wave behaviors. I'm going to put an asterisk next to that because when I get to the back I'll add another asterisk. I'll put C, next page. There are just a few things that all waves do, and light does these things. So on one hand, it's one of these things. It's curvy, it's got a certain wavelength, it's got a frequency and all that. On the other hand, it's like a little bullet just traveling through space, coming out of a, you could imagine there's a gun over here. This is a really bad gun I'm drawing. There's got to have a trigger for a gun. And this bullet shoots out of the gun. That would be like a laser or a flashlight shooting some light out. So what is light? Light's really hard to pin down. Number 5 says what we call light is just one kind of wave called electromagnetic radiation. So electromagnetic means that light has a component that's related to electricity, and it also has a magnetic component. You don't really have to know what that means or how it relates to light, except that that's the general name for waves that include light. Radiation, radiate just means to go out in all directions. So if you have if you have a person making sound, sound moves out in all directions. We radiate sound. If you have a heater or a radiator of a car, that gives off heat in all directions. If you have a light bulb, this is supposed to be a light bulb, shining like that, it gives off light in this direction, and this direction, and this direction. To radiate something just means to go off in all direction. A lot of times the word radiation, people think of bad stuff, dangerous stuff, and it can be, but it's not necessarily bad. So I'm going to show a picture now. This is showing the electromagnetic spectrum, and the color's not very good. This is a video of my wife's laptop computer. The important thing to note is right in here, see the word visible? This light is visible. There's the whole rainbow of visible light. That's what we can see. And right here, this is showing what the wavelength looks like. It says 0.5 times 10 to the negative 6. So the wavelengths of this, 0.5 is about a half. 10 to the negative 6 means 1 millionth. So it's about a half of a millionth is how long this, half of a millionth of a meter is how long that wavelength is. Really short wavelength. Now you can have even shorter wavelengths. Those are things called gamma rays, and you can have longer wavelengths. Those are things called radio waves, and there are all these other waves in between. But what's important one of the important things from this diagram is that if you look at the colors, red is on the longer end. These are all longer, these are shorter. So everything on the left is longer, everything on the right is shorter. Red is the longest wavelength of light, visible light. Then you have orange, yellow, green is right in the middle, blue, indigo, and violet. There's some people that say indigo doesn't exist, and I kind of agree with them. But it makes a nice word, Roy G. Biv, which helps you remember the colors. So red has the longest wavelength, violet has the shortest wavelength. All the other colors of visible light are somewhere in between. These pictures, these are just showing you how long the wavelengths are. The wavelengths of radio waves are about the size of buildings. The wavelengths of microwaves are about as big as us. A honeybee is about the size of the wavelength of infrared light. ultraviolet light. That's the stuff that can give you sunburn. The wavelength there is on the order of protozoans or molecules. Visible light is about the size of a pinpoint, and then we get even smaller with gamma rays and X-rays. And if you had to guess, I bet you could guess which end of this spectrum. It's called a spectrum because there's no break in it. It just goes from long to shorter to shorter to shorter to shorter, and there are really no edges to these categories of infrared and visible. One fades into the next. So if you had to guess which end of the spectrum is more dangerous, you could probably guess it would be the right end. X-rays, ultraviolet rays, gamma rays, those are all really dangerous. Those are the ones you have to watch out for. Visible light, not that bad unless you just stare at it for too long. Infrared, that heats us up. Microwaves, not so bad. Radio waves, those are all around us all the time and they're not too dangerous. So here's the really bad stuff, here's the not so bad. This is the stuff that lets us see. Now to the sheet before us. I want you to label some things, the different colors. This is visible light is right in here. I've labeled radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays. So the longest wavelength of light, right here, this is red. And a mnemonic device for these is the name Roy G. Biv. And I guess you don't have to write all these out, but I'm going to write red, orange, yellow, green, blue, indigo, and violet. So violet is the shortest wavelength, visible wavelength of light, and red is the longest visible wavelength of light. Now there are nicknames for the two ends of the spectrum. The long wavelength end, this end over here, people refer to as the, I'll give you two guesses. Is it the blue end or the red end? It's the red end. It's red, orange, yellow, all that stuff mixed together kind of looks reddish. And the shorter end, people refer to as the blue end. And that's just a simplification. There are these other colors in there, but they call that the red end and that the blue end. Now, what can we do with this? We have a couple of people. This is the next sheet, so flip your sheet over. A couple of people, person A and person B, and this is A, this is B. They're raising and lowering the ropes, so they're shaking these ropes. They're going to be creating waves in the rope. They're moving their arms up and down. Person A is waving frantically, and person B is waving the rope more slowly. And you're supposed to sketch the waves you think that will be produced. So see if you can anticipate what I'm going to draw here. A's rope is going to look something like this. B's rope is going to look something like that. So we haven't really talked about frequency, but we have talked about wavelength. It's the distance from one crest to the next crest. That's a wavelength. That's the symbol for it, but you don't have to know it. Who produces the longest wavelength? That would be B. That'd be the person who's shaking slowly. Who produces waves with the highest frequency? Now, we talked about frequency in terms of sound, and if this person's making sounds through a megaphone, and the sounds are going out in this direction, this would be one frequency. And if we had another person producing sounds and they look like this would be a different frequency. This would be a high frequency, this would be a low frequency. And that's because if somebody's listening over here, if you have another person who's hearing these sounds, the number of waves that reach that person per second is really low here. There might be one wave. Here's the wave front, here's another one. So this person might, if they were going to hear a click for each of these, they might hear click, 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 click. And if you had another person over here, these waves were coming to the person. If there were a click for each wave, instead of click, 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 it would be click, 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 click. So that's a higher frequency. There are more waves per second. So in the same way, there are more waves per second here. If somebody was standing over here looking, they would see more of these crests would reach them every second. This person, when these waves, or the end of the whip flip, slapped him in the face, instead of going slap, 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 it would be slap, slap, slap. So the highest frequency, that's A. This is high frequency. These are longer wavelengths. From there to there is a long wavelength. Now the point of this, all the important things are in bold. What colors are the hottest and coolest stars? What frequencies of electromagnetic radiation are most dangerous? Why? So let's go back to this, because that's going to get us to those. If those were waves of light, which waves would be more red and which would be more blue? So we're looking at these. These are longer wavelength, shorter or lower frequency. These are shorter wavelength. Going back to the previous page, the longer wavelength waves that we can see, those are the red ones. Red, orange, yellow, those are long wavelengths. From there to there is a long wavelength. The wavelengths get shorter as you go over this way to the blue end. So long wavelength light is red, short wavelength is blue. That means this is like red light and this is like blue light. So which waves would be more red? I just labeled it there. Which waves would be more blue? I already labeled that. We don't need to write anything there. Which person is more like a hot molecule? This person's shaking frantically. This person is moving more slowly. Hot molecule would be like person A. So now the point of this, what colors are the hottest and coolest stars? The hottest stars are, they're going to look like this person. They're going to be frantically vibrating back and forth. They're going to be giving off short wavelengths, and they're going to look blue. And the coolest stars, they're going to be not so frantically, vibrating back and forth. They're going to be sending off longer wavelengths, and they're going to look red. And that may seem backward. When a lot of times you look at an air conditioner control, it'll have red is hot and blue is cold. Same thing on a faucet. But if you are familiar with flames, ooh, this is bad. There's no good. Sorry, the color's not going to be good here. You can see red at the tip. That's a fairly cool part of the flame. I don't know if you can tell through the camera and the computer and the projector and all that, but this blue part of the flame, this is the hottest part. So blue flame is hotter than red flame. A blue star is hotter than a red star. And the reason people choose blue for cold on diagrams like that is probably either because ice is bluish and water is bluish, or because when people are cold, they aren't as red, and when people get hot, we tend to look redder. Okay, what frequency of electromagnetic radiation, what frequencies are the most dangerous? If you think about it, the dangerous ones are the ones with really high energy, like this person. So blue light is probably, it's on the more dangerous. It's not really dangerous, but it's on the end of the spectrum that's more dangerous. This is flipping back to the previous side. These waves, these are really high frequency, very high energy. I'm going to write that on here now. High energy. These are the dangerous ones. These are lower energy. These are not so dangerous, just in general. So what frequencies are most dangerous? High frequencies. Why? Because, let's see what I wrote. What did I write when I did this before? Because they have more energy? Okay. All right. Now, this next part may have to break off in just a minute. The next important question we're going to be getting to is, why is the sky blue? We'll get to that in a minute. But on the other side, I made an asterisk, and the asterisk refers to this spot. So back over here, I said that light is like a wave and that it exhibits other wave behaviors. See the next page. So these are 3 important wave behaviors, and I'm sure you're familiar with some of these. One wave behavior is that when light hits some water, this is air, this is water. I'll shade the water. When light hits the water, one thing it can do is it can reflect off the water. So B is called reflection. Another thing, you may not be familiar with this, but when light goes into water, it bends and passes through the water, and that bending is called refraction. Sound waves can do these too. A reflection is called an echo, refraction is bending of sound waves, that does happen too. And then the third thing, light, when it hits water, not all of it is just going to pass through. Some of it is going to get bounced around, and the bouncing around is called scattering. I think we'll get through why the sky is blue, and then I better stop. Okay, so this part is about scattering in the atmosphere. And might as well show the blue sky. Does that show up blue? Oh, that's nice and blue. So the sky is blue for a reason. If you look at these three arrows, the question says, imagine you're shooting arrows at bags of sand. Your arrows are shown on the right. Choose which arrow you think will be most likely to penetrate the bag. And then choose the arrow that will be most likely to bounce off. So if you had some kind of a sack of grain or something like that, and this is the sack, and all three of them hit this bag, which one do you think would be most likely to bounce off? Probably B. This is the one that's going to bounce off. And the one that's most likely to go through is probably C. The B is the curviest. It's not going to go through very well. C is pretty straight. It's straighter than the other ones. So B bounces off, and C penetrates. It passes through. Whoop, can't see what I'm writing here. Bounces off, passes through. Now, the fine print. If the air is full of little things, and it is full of little things, you just can't see all those little things, which color of light do you think is most likely to be able to penetrate the air and least likely to be scattered, red or blue? So if we look at this, this is the red end of the spectrum. I'm just going to turn this into an arrow now. Whoop. Turn that into an arrow. And this is the bluish end of the spectrum. I'm going to pick indigo, but I could pick blue. I'll just use blue. Of those two, red is the straighter arrow. Blue is like the one that I just said would probably bounce around. So of the two ends of the spectrum, the red end and the blue end, this end goes through the air pretty well. This end bounces around in the air and gets scattered. So in this example, I'm showing light passing into water, but the same thing happens in our atmosphere. When light goes through our atmosphere, scattering occurs, and the colors that get scattered are the blue ones, the short wavelength ones. So the answer, the question there is, why is the sky blue? And the answer is, when sunlight passes through our atmosphere, the shorter, and in parentheses I'm going to write bluer, wavelengths of light get scattered all over sky. So that's what the sky looks like. Now if you didn't have a bunch of stuff in the atmosphere, then those little arrows that I was just drawing, those arrows, would be able to go right through. And they wouldn't get bounced around, so when you looked up at the sky, you wouldn't see any color at all. This is a picture of the sky on the moon. This is daytime on the moon. You can see the Earth off in the background. So this is the surface of the moon. The sun is somewhere up there, casting light down on the moon's surface and also casting light on the Earth. But the sky is totally black because there's no air around the moon. So those rays of light, when they go through the moon's atmosphere, there is no atmosphere. So they do not get bounced around and there's no color to the atmosphere. This concludes part 1.